Okay fellows out there, welcome to lecture 10, module 1 of my video series on introduction to data structures in C. Today we will go through some code snippets and get to know our compiler a little better with respect to the concepts that we had covered in my previous lecture. Okay, go through this code, predict the output, verify that, and let's come back and look at let's analyze this piece of code. Okay then. This main function basically has one single line. Okay, that's printf %d printf nested inside it. Okay, so how does the C compiler work? First, it gets into the innermost bracket and basically decodes this. So what does this print out? It prints out %d, that it prints out a 1, and from after that it goes to the next line. So it prints out a next line there. Okay, and after that the compiler basically comes back to the original printf, that is the outermost printf, and starts executing it. So it has a %d and next something out here plus 1. So the main question is, what does printf return? So printf basically returns the number of characters that it has printed out. So in this case it has printed a 1 and a next line, so the output would be 2. So 2 plus 1 is 3. So the output of this code is basically 1 and 3. Okay. Okay guys, here is the second bit of code. Okay, so predict the output, compare it with the results that you get, and come back and have a look at the analysis of this code. Okay, out here I have a macro defined here, hash defined a10, and then I have my main function, and inside the main function there's another macro. Here I use hash define a is equal to 50, and then I print out the value of a, which is what, 10 or 50. Okay, so it's 50, and the takeaway from this particular code is this is permitted. So you can have multiple definitions of macros or constants, and both outside and inside the main function. Okay, this is perfectly all right. The code compiles and runs, and the output that you get is 50. Okay, so what would be the output of this piece of code? Okay, so predict it and come back, verify, come back, and let's analyze this. Okay, so here I have a character pointer char star p. You remember pointer, special variables which can store yes, addresses. Okay, so I have a character pointer which can store an address of what type? Of character type. Okay, and then I have a printf. Here I printf two integer values. One is size of star p and the other one is size of p. So what is size of p? Size of p is the number of memories allotted to store, okay, p. And what is p? P is a place where the character gets stored. Okay, so p is a place where the address of a character is going to get stored. So what would be the size of memory required to store an address of a character? Okay, so that's 4, right? And then I have size of star p. Star p is value at p. So what are the values that can be pointed using p? Okay, these are characters. So what is the size of allocating memory to store a character? It's 1. Okay, so basically the output would be a 1 initially, that is this. Okay, and then a 4. Okay, so if you have predicted this and got it as the output, bravo. So let's go to the next piece of code. Okay, do the activities, come back, and let's analyze it. Okay, fine. If I look at into this main function, then I have just 2 lines. First one is an array of integers, an array called a, which can store how many integers? 10 integers. So the size of the array is 10, and the type of array is, it's an integer array. and then I have a printf command. I have %d star a plus 1 minus star a plus 3. So what is basically going to get printed out? Okay, so effectively what happens out here is I have x plus 1, whatever is star a, it doesn't matter, I'll just treat it as some value x. So what happens is x plus 1 minus x plus 3. So this x and this x gets cancelled. So even though I do not know what is star a, which is the value at the base address of a, that is a0, okay, I still can predict the output as 4, and if you have got this right, okay, congratulations. Okay, so here is the next code. Go through it, do a dry run, predict the output, and let's analyze it. Okay, so here I have a main function, but before the main function I have a macro, okay, in the global definition part. Okay, I have hash defined product a comma b as a star b. So wherever the compiler basically finds this product a comma b, it replaces it with a star b. Okay, so that is how macros work. Fine. So then I have the first line in my main function, which is int x is equal to 3 and y is equal to 4. So two integer variables x and y are being initialized by 3 and 4 integer values respectively. Okay, so then I have this line where I have product x plus 2 comma y minus 1. So basically what happens is, instead of this gets replaced, so it becomes a plus 2 into y minus 1. Okay, so what is that in x? So it becomes 3 plus 2 into y minus 1, and what is there in y? Y is 4, so let me put it as 4 minus 1. Okay, so remember the rule of precedence. Okay, we know that the multiplication has higher precedence than subtraction and addition, so this gets executed first. So 4 into 2 is 8, 8 minus 1 plus 3. So now since addition and subtraction have the same precedence, okay, the evaluation happens from left to right, so it becomes 7 plus 3, which is nothing but 10. So that is the output that you get for this piece of code. Okay then. Okay, that's what is been explained out there. Okay, so look at this piece of code. Okay, so predict the output. Let's come back and see what it is. Okay, for those who have not seen this and are seeing it for the first time, it is if this is true, return B, else return C. So it is a kind of a if then command. Okay, so if whatever out here is true, then this particular thing out there returns B. Okay, so if this is true, what comes out of this is B. Okay, or if when it is false, what comes out is C. So that is how this if then shortcut works in C. Okay, so taking this into account, here I have so star A, address B and address A. So what is A? A is 0. So A is 0 means it is false. So true is 1, false is 0. So if this is false, okay, so what gets output? Output becomes star ampersand A. So since this is false, this comes out. Okay, and if you look at this piece of code, here A is again false, so what comes out is again C. So it becomes star ampersand A is equal to C. So this star value at an address of does get cancelled out, so it basically becomes A is equal to C. So A gets the value of C. So C is 3, so A becomes 3. And when I print them out here, when I print it out here, So it basically, since A is equal to C, is what happens to this line of code. Okay, what gets printed out is the value of C, which is 3, the value of B, which is 1, and the value of C again, which is 3. So the output that you get is 3, 1, 3. Okay, so that is what gets printed out. Fine. Okay, so let's go to the next piece of code. So do the activities, come back, and let's analyze this code from there on. Okay, so let's look at this piece of code. Okay, so I have a character array which is being initialized with 1, 2, and 3, and then I have a character pointer which points towards the array, and then I have address of P is equal to address of A, print out same, else print out not same. So what gets printed out? So are these the same? In fact, they are not, right? So not same gets printed out. Okay, why is it? Because P is equal to array here would have given the same result. Okay, address of A. But what am I doing? I'm substituting the address of P. Is the address of P equal to the address of A? No. P is been stored somewhere. P is a pointer. It is stored in some different memory location. Say it has a address XXX, and then array is stored in another part of the stack, might be which has the base address YYY. So whatever you do inside this and this, these two cannot be the same. Okay, so that's why even though I am telling star P is equal to A, that the address the value at P is pointing to X, I am not basically comparing this with the value at P, but I am comparing this with the address of P. Okay, I am comparing the address of the array with the address of P. So that cannot be the same. So what gets printed out is not same. And in fact, if you want to print same, then you have to replace this line of code with P is equal to address of A. That is, the content of P is the content of P. This is P. Is it equal to the address of A? And the value pointed by P is basically the first element of the array. So it's not star P, it is P is equal to address of A, mind you. Okay, so that pretty much summarizes the analysis of this piece of code and the results that you get out of it, which is not same. Okay, so here is another bit of code. Okay, go through it and then come back and let's analyze what is happening out here. Okay guys, so let's take it one line at a time. Okay, so what is given out here is a main function, and I have an integer variable A, then I have a character pointer, and then I'm typecasting the address of this integer to a character pointer and then storing it in that particular. So I'm basically trying to store the value of integer array to a character pointer. Okay, the address of an integer array to a character pointer. Okay, so ideally this should have been int, but it is not, it is character. So I'm typecasting the integer to a character and then storing the address in this pointer X. Okay, and then I'm using a value 512 to basically store in the address allotted to A. Okay, and then what am I doing? I'm basically printing out what is X. X is the character pointer, so I'm printing out the first element of the first byte. So basically it's a character pointer, so it does byte by byte pointing. Okay, so it references byte by byte since it's a character pointer. Okay, so I'm basically printing out, I am assigning 1 to the first byte and then 2 to the second byte. Okay, so what actually happens out there. Okay, so in my compiler, character is being given as 2 bytes. Again, I told you this is compiler dependent, and integers are being given 4 bytes. Okay, so the first 2 bytes take up 1 and the next 2 bytes take up 0 2. Okay, and then I print the value at A, okay, or the value stored in A. So both are basically pointing to the same memory location. Remember my lecture on unions, and I had said that might be you can have access to the same memory location with different type of data referencing if you are using unions. So this is basically a classical case of that scenario. What was done there is very similar to what is happening out here. I have a memory location of 4 bytes, okay, say 2 bytes plus 2 bytes, okay, and this memory location is being now referenced or being accessed by two people. One is A, which is a character variable, integer variable, and another one is star x, which is a character pointer. So when I use A, it basically takes all the 4 bytes together and gives me the information, okay, that is 512, or stores that particular thing. Whereas when I use star x, it references 2 bytes at a time, because in my compiler 2 bytes are given for the character. So first it takes 2 bytes, and you can basically read and write into this 2 bytes of memory, and then when you increment this, it points to the next 2 bytes, and you can basically read and write into this memory using that pointer. So that's basically what is happening. So I'm storing 1 and 2 in this memory location of 2 bytes, okay, 1 and 2 using the character pointer, and then I am reading it out using an A. So I am reading it out together. Okay, so what do you think would be the output? Okay, so the output would be 513. Okay, the output would be 513. Again, depends on your operating system. So Windows follows Little Indianness. So you know that the lower bytes are stored in the upper memory locations, and the higher bytes are stored in the lower memory locations. So basically what it has done is it has converted this 1 and 2 into a bit pattern saying 0 0 0 0 0 1, and then 2 is 0 0 0 0 0 1 0, something like that. And it has basically taken this bit pattern and converted it to a number and read it as a number together, which has resulted in this 513. Okay. So if you are having a machine which follows big Indianness, then probably you might have got it as 258, because this gets swapped out here and this gets swapped out there. Okay, so that's what is happening in this piece of code. So you might have either got it as 513 or 258 and would be wondering what is actually happening in this piece of code. So that explains quite a lot, I feel. Okay, looking to the, okay, so that's the explanation for it. Okay, so that is what I was trying to explain you. This is the bit pattern that happens, and if you read it together, this number basically turns out to be 513. Okay, so let's look into another piece of code and see what is happening out here. Okay, so do the activities, let's come back and analyze what is happening. Okay fellows, so you must be wondering what is out happening. You might have got a weird answer. Okay, so let's analyze what is happening. So in this main code, I have an integer variable c which takes the value 5, and then I have just a one liner which is %d/n %d %d. Then I have c bit shift to the left by 2 and bit shift to the right by 2, and so on. Okay, so in C we have something called as a comma operator. So this is something that I would like to highlight at this juncture. Okay, so how does this comma operator work? So basically it starts decoding everything from left to right. Okay, so this piece of code runs, or this parameter gets evaluated first. So it is as good as writing C is equal to C right shift it by 2. Okay, so when you know that as a right shift operator basically implies dividing by 2 raised to whatever is given out here, so it is dividing C by 2 raised to 2 because 2 is given out here. Okay, so C gets divided by 4 and the value of C is 5, so this basically results as 5 divided by 2 raised to 2, which is nothing but 1. Okay, because C is an integer. Okay, and you know that this is C is equal to C right shift by 2. Okay, so C becomes equivalent to 1. Having done that, C getting the value of 1. Okay, so the next bit of code gets executed. Okay, that is the second part, which is C right shift by 2. Okay, so that piece of code gets executed. Okay, out here. Okay, so what was the value of C? The value of C was 1, and now left shift is nothing but multiplication by 2 raised to whatever number is given out here, that is 2. So this results as C is equal to C left shift by 4, sorry, left shift by 2, which is nothing but equivalent to C into multiplication of 2 raised to 2. So C 1 into 4, so the resultant value is 4. So at the end of this, C gets the value 4. Okay, and what happens next? Next is nothing, just C is kept as it is, so it gets printed out. So at the end of this full execution of this comma operator, C becomes 4, so C gets printed out here, same thing gets printed out here, and same thing gets printed out here, because this is nothing but C is equal to C left shift by 2. Okay, so the result that you get is 4, 4 and 4. Okay, so that's what happens in this piece of code. Okay, so let's look at another piece of. So here which of these things are valid? Remember my last lecture on enums, so use that concept and see and tell me which of these concepts are good and what actually happens. In fact, all of them are right, all the five of them are right. So you can have a enumerator cricket as a tag, and then you can have the constants or enumerator list, and then you can have instance of it. So C is the instance of cricket. Without any instance, still valid. With instance and a value initialization in between is still okay. So this becomes 0 and this becomes -4 and so on. Okay, so this is also valid. What about this? Again an instance, but the tag is C. Okay, and again an enumerator with the tag C and no instance, again it's perfectly valid. And about this, as we said, without tag but just the list, no instance, still valid. So that can happen. Okay, so all the five of them are correct and are very valid commands in C language. Okay, now so look at this piece of code and let's guess what is happening out here. Okay, so here I have two variables of type float, f and g, and then I have an enumerator which doesn't have a tag and which doesn't have an instance, and then I print out k plus plus, and then I do something on f. Okay, that's fine. And then I have f mod g. F is a float and g is also a float, so, and then I have f mod g. Okay, this is mod g and f mod g. Okay, so that's what is happening. So if you look closely, this is a valid line of code, this is valid, but you have problems with this. You cannot basically change the number associated with the constant. So this is not permitted. So you get an error out here. That's the first thing. The second error that you probably might have got is bit shift operator or shift operators are not valid for floating point numbers. These are only for integers. So probably you might have got an error on that as well. And the third error that you might have got might be with respect to this, because as I told in my previous lecture, mod operators are only for integers, okay, but f and g are floats, so you get an error for this. Whereas this is perfectly valid. So for floating point modulo, we have a built-in function called as fmod, which takes in two floating point numbers and does the modulo operation. So the right output would have been 3 errors as the output of this code. Okay, so that's what is given out there and is been explained. Okay, fine. So that's all for today, folks. Hope you have enjoyed this lecture, and stay with me for my next video lecture on this web series. Thank you.